Okay, in today's class, we are going to talk about motion control. So today we will start controller analysis and how do we control robot. And there are multiple aspects to it. So first, let me talk about what do I mean by controlling. So we are going to talk about robot control. So what do I mean by robot control? Robot control is actually making sure that the robot behaves the way you programmed. Say if you want your robot to go from point A to point B at certain speed, you want to make sure that the robot goes from point A to point B at that desired speed. Now there are two ways typically a controller is achieved. So there is something called as the open loop control, and there is something called as the closed loop control. So think about it like this. What do I mean by open loop? Say I'm continuously teaching without getting any feedback from you, whether you understand the material or you don't understand the material. That is me going in open loop. However, every time I stop and ask for feedback, like, hey, have you understood this? Do you have any questions about this? Etc. etc. That is going in closed loop. So when you talk about the control, there is something called as the open loop control. So there is open loop control. So you have input and you have a robot, or also called as plant, or this is actually the robot. And then you have output. This is called as open loop control. And the alternate to this is closed loop control, which means what you have is you have a plant, you have some input, you have some output, and then you have a feedback that goes from the output. And usually what you have is you have some sort of a summing junction where you have this feedback. This is called as the closed loop. Now, a very simple example is if you look at the 3D printers in the Innovation Hub, or for that matter, the 3D printers that you bought or you're using, they have something called as the stepper motor. So in stepper motor, you supply a pulse width and the motor goes to a desired position, but you don't have any ways of verifying if the motor has reached that desired position or not. So there is no feedback. But sometimes what you have is you have a motor. Say you have a motor, and then at the end, what you have is you have an encoder. So you have some sort of encoder. So it could be a Hall effect sensor, or it could be an optical encoder. Question? I'll show you what that means. You have encoder. So basically it is some sort of a feedback. A classic encoder, it's like you have gradations and you have photodiode on the either side of the gradations. So what you have is, if you look at the side view, this is sort of the slotted disk, and you have a light source and you have a detector. So what that means is as this disk rotates, you are gonna get some sort of a input or pulse width. So you know exactly how far that wheel has rotated. So you have some sort of a feedback. So you have this encoder and you have this motor that is connected to a controller. This assembly is called as servo. So a servo system has the actuator and the feedback element integrated. So if you look at the small robots, usually they can run on the stepper motors, but unfortunately they can be only run in open loop. For example, the 3D printers that you see, they are run in open loop. So you set a command and hope that command gets executed. The motors move by the amount that you ask them to move. But if you have an encoder or some sort of a feedback, then you close that loop. So you know exactly where the output is, and depending upon how that motor is achieving the desired location, also called as the set point, you can tweak the gains, or you can amplify the signal, you can decrease the signal, and so on and so forth. So at this point, what I want to tell you is you can have an open loop control or you can have a closed loop control. Next thing, and this is super important, is what I want to talk about is the notion of stability. So stability. So what do I mean by stability? And let me explain this by means of an example. So imagine we have a ball that is rolling on a flat surface. Imagine we have a ball that is rolling in a curved surface, and so it's like a bowl, and we have a ball that is rolling over a surface which is concave. So now I want you to understand, like, what happens if this ball gets moved or gets perturbed. So what happens if I were to push this ball towards right or towards left? You understand that in this particular case, I push or nudge the ball left or right. What's going to happen is this ball is going to go and sit either on the left or on the right. What's going to happen in this particular case? If I nudge this ball left or right, you will notice that this ball will kind of go back and forth and oscillate. But again, finally, the ball will settle where the energy is minimum. Everyone understood this? So minimum potential energy. What's going to happen here? If I nudge the ball here or here, recognize that this ball is going to go all the way over here and it's never going to come back. So these three things can be explained with the notion of stability. And notion of stability is super duper important. So I'm going to repeat this one more time, because you will study this in all the classes. You will study this in dynamics and controls, robotics too, system dynamics, system control and optimization, transforms and modeling, foldable robotics, everywhere you will study this. Remember, what do I mean by stability? So let me say that me and my friend, okay, we argue, okay, we argue, but then what we say is, okay, let's agree to disagree and reconcile. Let's agree to disagree and reconcile. That is neutral stability. If I argue with my friend, but we argue and fight so much that we decided to go our ways and say, I will never talk to you again, our friendship is over, that is unstable. And if I argue with my friend, but at the end we say, forget it, I was wrong, you were wrong, both of us were wrong, let's come back, that is asymptotic stability. Neutral stability is going to a different point but still remaining stable. Asymptotic stability, asymptotic stability means you are coming back to where you started, and this is unstable system. Now let me ask you, what happened when we simulated the robot arm? You recognize that robot arm that we simulated in assignment 4 showed some sort of unstable behavior. It didn't come back where it started. Say for an example, R and R dot value. It just increased as the time increased. So clearly that system was unstable. Let me give you another example, and this is very important. And I want you to pay attention. So if you have a pendulum, which is like this, then you agree with me that if you perturb it, so this is another important word. So disturbance, also called as perturbation. So if you disturb, what's going to happen? This is going to go back and forth, and finally it would come back to where it started. So this pendulum, upside down pendulum, is asymptotically stable. On the other hand, if you have an inverted pendulum, please understand, as soon as the pendulum is perfectly vertical, everything is balanced, then perhaps it will stay like that. But as soon as there is small perturbation, it will go down and it's never going to come back. So this pendulum is unstable. Everyone understood this? Now the question is, same pendulum, what dictates? In one case, that pendulum is asymptotically stable. In other case, that pendulum is unstable. So concept of stability is always associated with returning to initial position, not returning to initial position, or finding another equilibrium. So I need to write this down. So neutral means finding another equilibrium. So asymptotic stability means coming back to original. And unstable means never coming back. Everyone understood what this is? Now let's try to add some math to it. Okay, and the reason this is very important is, why do we want to control? Many a times the robotic systems that we see in practice, they are unstable. So you need to add some sort of controller so that that robotic system can be controlled or can be moved from point A to point B and so on. So first and foremost, let me give you a very simple example. Let me give you what it means in terms of mathematics. So think about that you have a differential equation, x dot is equal to ax. This is the differential equation. Now this differential equation is called first order differential equation. Why this is called as the first order differential equation? Because you have dx by dt is equal to ax. Here, and I'm going to write this for the first time, you have x of t, which is the dependent variable, and t, which is time, is the independent variable. Now the question is, if I want to solve this differential equation, what do I mean by solving this differential equation? And you have studied this in your differential equation class. Solution of a differential equation means determination of a function. Solution of differential equation is determination of function or functional relationship between the independent variable, in this case time, and the dependent variable, which is x. So say this is some sort of this functional relationship. And this is super important. At the end, how do we know if this function that we have, I'm going to call this function f of t, and this could be anything. How do I know that this function f of t is the solution of differential equation? How do you know anything is the solution of any equation? Go ahead.
It's testable.
Yeah, just plug those in and see if the left hand side is equal to right hand side. So if I substitute this f of t on the left hand side, what do I have? I have d by dt of f of t is equal to a times f of t. If my left hand side is equal to right hand side, if this condition is satisfied, then indeed that is the solution of differential equation. Let me tell you, whatever you studied in differential equation class, you probably used the linear differential equations that can be solved in closed form, or that you can derive mathematical expressions. But many differential equations you cannot solve in closed form. So what you need to do is you will have to use some sort of approximate technique. And this is the basis of approximation. What you do is you assume a function, substitute that function on the left hand side, substitute that function on the right hand side, and for some reason, if the left hand side is equal to right hand side, then you got the solution of differential equation. That is the trial and error technique that is very commonly used while solving the differential equations. But for this particular differential equation, so you have dx by dt is equal to ax. Differentiation is derivative. If I want to find out the solution, I need to do integration. So what I'm going to do is I'm going to perform the integration. So please note, I'm going to take x's on one side and t's on other side. Please note, a is a constant. So what I would do is I would integrate left and right, and integration of 1 over x is ln of x. Integration of a dt is at plus constant of integration c. Now what I'm going to do is I'm going to take the exponent on both sides. So I will have e to the power ln x, that gives me x of t, and this gives me e to the power at plus c, which can be written as e to the at multiplied by e to the c. E to the c is a constant, c is a constant, e is a constant. So c power e to the power c is a constant. So this can be written as another constant, e to the at. So what it means, the solution x of t is a e to the power at. Are you with me so far? Now, if you want to check if the solution that we obtained here is indeed the solution or not, then what we should do is we should substitute that in equation 1. What is the derivative of a e to the power at? It is small a, capital A, e to the power at, that you get on the left hand side. And on the right hand side, you have a e to the power at. So your left hand side is equal to right hand side. So this indeed is the solution of the differential equation. Everyone understood this? Any questions? Yeah.
Sir, can you repeat where last section we had E to the R, how we got A, E?
C is a constant.
Correct.
E is a constant. So constant to the power constant is another constant. So e to the c, I'm replacing that by a. Everyone understood the last part, that xt is equal to a e to the power at is the solution of the differential equation. Why is that? Because if you take, everyone understood? Yes, no? So what I did is I did x dot of t. And I know probably you understood, but I need to do this because this will be very important when we try to solve the differential equations using some type of substitution. So that this will become a e to the at. Now please note, what is axt? Axt is a e to the at. So as you can see, the left hand side is equal to right hand side. That's why this, what we have found out, is the solution of differential equation. Now this brings us to some interesting observations. Now what I want to do is, I want to ask you this question. Let's plot. This is very important, so please understand. Let's plot time xt. Let's plot time xt. Let's plot time xt. Now in first case, I'm going to assume a is equal to 0. In my first case, small a is equal to 0. You agree with me, when my small a is equal to 0, for all time t, from t is equal to 0 to t is equal to infinity, this is going to be a flat line. Are you with me so far? Any questions here? Now, let's assume value of a is less than 0. Value of a is less than 0. So can you see that this is going to be line like this, because this will be e to the minus at. So you start with a, but as time goes on, it's going to decrease. You agree with me? What happens here? If my a is greater than a, small a is greater than 0, then you agree with me, this is going to be like this. So e to the at. Agreed? Now what I want you to do is, I want you to compare this with the pendulum problem that I just showed you over here. When the system has neutral stability, what it means is you start with point A, you displace it, you find another equilibrium, you displace it, you find another equilibrium, and so on. When the system is asymptotically stable, that means as time goes to infinity, system goes back to its equilibrium. In this case, it's a 0 position. System goes back to 0. When the system is unstable, you perturb the system and system response grows. So in first case, the system response, when the system is neutral, so this is neutral stability. This is asymptotic stability. and this is unstable system. So these three are super important concepts. Yes.
You said that asymptotics and stability comes to the original position.
Yeah. So in this particular case, basically it will go down to zero, because a zero, it start with assume a is equal to zero. It will go down to zero.
Like a equal to 0 is the first one.
Yeah, so I just give you an example to draw. So asymptotic stability means the response, it goes to asymptote. So basically it decreases. That's what it means. There are small nuances, basically whether you are going towards a fixed point or you are going to an equilibrium orbit, but we'll talk about it a little bit later. But right now, what I want you to understand is the only thing that is governing the behavior of the system, the only thing that is controlling the behavior of the system is the value of A. Are you with me? This A is controlling what is happening to the system. Now, what I want you to do is, I want you to think about, and this is a very interesting extension. So what I'm going to do is, I'm going to try to write this equation x dot is equal to ax is a scalar equation. Why it's scalar equation? Because x of t is just a single variable. Now what I want to do is, I want to write this equation slightly differently. I want to write this as a vector equation. Vector means I have x1 of t and x2 of t. And this is very important. So everyone please pay attention. So I'm going to write this equation something like x1 of t is equal to a1 x1, x2 of t is equal to say a2 x2. But note, this equation can be written down in a matrix form, and this matrix form can be written as x dot of t, x2 dot of t is equal to a1, a2, x1, x2. Are you with me so far? Now remember this equation. What happens if my a1 and a2 are zeros? You agree with me? If my a1 and a2s are zero, the system is neutrally stable. Do you agree with me? What happens if my a1 and a2, both of them are negative? System is asymptotically stable. If my a1 and a2 are greater than zeros, system is unstable. Do you agree with me? Everyone understood this? What is a1 and a2? A1 and a2 are nothing but eigenvalues of this matrix. Remember eigenvalues? So, and if you don't remember what eigenvalues and eigenvectors are, I will solve this here. So eigenvalues and eigenvector problem is basically ax is equal to lambda x. What you do is a minus lambda I x is equal to 0. And how do you find out the eigenvalues? You say determinant of a minus lambda I is equal to 0. Remember this? Yes or no?
Yes.
No? Okay, this is serious. Close your eyes and tell me how many of you don't know about eigenvectors and eigenvalues. That's why I'm saying close your eyes so you won't know who knows or no. Okay, all right. Okay, all right. So let me tell you. Okay, so if you have a matrix, matrix is bunch of numbers stacked together. A, B, C, D, or 1, 2, 3, 4. This is a square matrix. You can have a rectangular matrix 1, 2, 3, 4, 5, 6. You can only find eigenvalues and eigenvectors for square matrix. So eigenvalues and eigenvectors. So what I want to tell you is what is the interpretation of eigenvalues and eigenvectors? If you haven't studied eigenvalues and eigenvectors before, please try to understand. They give you the most important component of the matrix. Now, how many of you don't know what eigenvectors are? Okay, all right. So think about it that everyone knows what a matrix is, right? This is a matrix. And what I'm going to do is I'm going to multiply this matrix by a vector X. So what do I mean by multiplication by vector? So I have this matrix 1, 2, 3, 4. And what I'm going to do is I'm going to multiply this by a vector 1, 1. Can you see that is 2 rows, 2 columns, 2 rows, 1 column. So do you agree with me? Finally, I'm going to get 2 rows, 1 column. So I will get 1 plus 3, 2 plus 4. So I would have 4, 6. Do you agree with me?
Yes.
So when I performed multiplication by a matrix, what happened to the original vector? So let me plot this original vector. My original vector is 1, 1. So this is my original vector. So this is my 0, 0. I go 1 unit in X direction. I go 1 unit in Y direction. That is my end point. So I'm going to call OA. So this guy is my vector OA. So starting from O going towards A. Do you agree with me?
Yes.
Now, when I performed the multiplication, what happened? The multiplication actually gave me 4, 6. So I went to 4 and I went to 6. So I went to 4 and I went to 6. So basically, this became OB. Do you agree with me?
Yeah.
So what happened? The matrix multiplication stretched and rotated the vector. Matrix multiplication, and this is a very important statement. So when you multiply a square matrix by a vector is stretched and rotated. Now, why is this needed? This is needed because, if for an example, if you are looking at a screen and you want to change the camera angle and all that kind of stuff, then you can actually perform this type of stretching and rotating operation that would actually magnify the image or distort the image or so on. Now, the eigenvalue problem. Now, imagine a vector. Imagine a vector. When you multiply that by the matrix, you get the scaled version of the vector. So for an example, think about it. So what you have is initially you had vector OA, and what I do is I multiply with that matrix, but after multiplication, what I have is I have a scaled version of vector OA. That scaling is nothing but the eigenvalue, and that vector is called as the eigenvector. Now, why this scaling and eigenvector is very super important? Because this is the crux. Eigenvalue problem is if you have a vector x, you multiply that by ax, what you get is you get lambda times x. So please note, x is a vector, same vector. Once you multiply that by this matrix, you get the scaled vector. If this condition is satisfied, then lambda is a number, it's a scalar, it's called as the eigenvalue, and x is called as the eigenvector. Now, what is the other way of looking at this? If you look at this problem, you can say something like you have this matrix A, and what I'm going to do is basically lambda x is nothing but considered as the decomposition of matrix. So you can perform an eigen vector decomposition, and that gives you the basis vectors. But what I want to tell you at the end, eigenvectors and eigenvalues, they give you the crux of the matrix. So eigenvalues are super important when you study the matrix algebra. In this particular case, if I want to solve the eigenvalue problem, my matrix A is A1, 0, 0, A2. So I would do A minus lambda I. I would do the determinant, equate it to 0. So what I have is A1 minus lambda, 0, 0, A2 minus lambda, determinant is equal to 0. So this equation is going to be A1 minus lambda, A2 minus lambda is equal to 0. So my eigenvalues are going to be lambda is equal to A1, lambda is equal to A2. So these are the eigenvalues.
I is the identity vector, right?
I is the identity vector. That's correct. So what this is saying is if you have a rectangular system of equations, a differential equations, and if your eigenvalues are negative, then the system is asymptotically stable. If the eigenvalues are 0, system is neutrally stable. And if your eigenvalues are positive, system is unstable. Yes.
So, I don't know, in my differential classes, we use eigenvalues to build and develop, like, so fields are.
Yes, you
robots
can.
essentially
Yes,
control these
basically you
slope
can.
fields.
Yeah, you can use eigenvalues to find the slope fields.
Oh,
So yes,
Like, what if we get a parabolic curve syndrome?
parabolic curve.
Like one positive and another negative.
Okay. If you get one positive and one negative, then the system is unstable. So both the eigenvalues should be negative.
Oh no, means I was talking about the what if it's not a continuous curve?
Continuous curve. I don't understand the question, but I'll take an example where one eigenvalue is positive and one eigenvalue is negative. That way I can explain what is going to happen. Now, this is a very, very important statement, and I want you to remember this. If eigenvalues are negative, system is asymptotically stable. If eigenvalues are 0, the system is neutrally stable. If eigenvalues are positive, system is unstable. So now what I want to do is I want to actually take a very simple example, and believe you me, this is the only thing that you should remember from your entire differential equation class. So yes.
Okay, so you said that if one is positive and one is negative, it's unstable. But what happens if one is negative and one is zero?
One is negative and one is 0. So the system is stable,
Okay.
but it's not neutrally stable or asymptotically stable. Basically, one mode is neutrally stable. So in other words, part of the system is neutrally stable, part of the system is asymptotically stable, and depending upon what part you excite, the system stability is governed.
Okay.
So this actually will require a little bit more discussion, but I'll do that. Just believe, bear with me for a second. So now what I want to do is, here is the simple, super duper simple technique to solve any linear differential equation with no forcing. So for an example, if you have a differential equation given to you of the form mx double dot plus kx is equal to 0. This is the differential equation that is given to you. This is the differential equation, which is a very famous differential equation describing the motion of a mass m attached to spring of stiffness k. This equation comes from application of Newton's law. Force is equal to mass times acceleration, and you get this equation mx double dot plus kx is equal to 0. Now what we need to do is, step 1 is identify the states. So first step, identify states. So please note, this is a second order differential equation. So if you have a second order differential equation, what you are going to do is you are going to have two states. So the first state is going to be x, and the second state is going to be the derivative of x, which is x dot. So what you will do, you will start with the state with the 0th derivative. Can you see that here there is no x dot? So this is the 0th derivative. So this is the first state. You have the derivative of the state. This is the second state. You have to write down the equation in state space. You have to write down the equation in the state space. And we have done this when we used Euler-Lagrange, but I just want to show you what is to be done. You will write this equation x d by dt of x and d by dt of x dot. So please note, you have x state here, the second state over here. D by dt of x is x dot. Do you agree with me? D by dt of x is actually x dot. And d by dt of x dot is x double dot, which is nothing but minus k by m x. I'll give you a minute to think about it. So here, note x double dot is equal to minus kx divided by m. Everyone understood this? So I got these two equations. So now I can write this equation into a state space form x dot d by dt is equal to a x dot. And my matrix A is going to look at, so check this out, it's going to be 0, 1, minus k by m, 0, x dot. This is d by dt of x dot. Are you with me so far? Now, if I want to decide whether this system that is shown over here is stable or neutrally stable or asymptotically stable or unstable, what I would do is I would find out the eigenvalues of this matrix. Once I find out the eigenvalues of this matrix, if those eigenvalues have negative real parts, then the system is unstable. If the eigenvalues have positive real parts, the system is unstable. And if the system has 0 real parts, then the system is going to be neutrally stable. Yes.
How do we know where to place the values in the matrix?
So I give you an example. So you have a spring of 5 Newton per meter stiffness, and you have a mass which is 10 kilogram. So you'll place 0, minus 5, 10, 1, 0.
Okay, so this is what you're giving us is a formula.
Yeah, but this is how we got that formula from. This is the basic differential equation.
Right. But what I'm saying is, before all that, when you have the matrix 0, 1, negative k over m, 0,
Mhm.
how do we know that the 1 goes in that place and the negative k over m goes in that place?
Okay, check this out. So if you multiply
A1 and A2 in the wrong spot.
here, no,
Yeah.
they are in the right spot. No, they are in the right spot. This matrix does not have has purely imaginary eigenvalues. So bear with me for a second. So if you think about this equation, so let me answer the very first equation. D by dt of x is 0 x plus 1 x dot. D by dt of x dot is equal to minus k by mx plus 0 x dot. So when you actually write this, you're going to get 0, 1, minus k by m, 0. Okay. Now I want you to try this. So what you will do is you will go to MATLAB and say EIG 0, 1, -5 by 10, 0. And when you do this, it will give you eigenvalues. And please note, they will have zero real part. Those eigenvalues will be purely imaginary. So eigenvalues, imaginary. What that means is zero real part. So what that tells me is that system is neutrally stable. Now let's try to identify if that neutrally stable behavior can be realized physically. So what I do is I pull this mass, let it go. There is no damping, there is no friction. Then you will realize that this mass will continue to oscillate back and forth, back and forth, back and forth, and so on. If there is no friction, if there is no energy dissipation, then that mass will continue to oscillate back and forth, back and forth, back and forth. This is how a neutrally stable system would look like. Now let me add one more thing to it. If I add a damper, now my equation, so let me add a damper. So adding damping. So what you have is, you have mass, stiffness, and I'm going to call this C, which is damping. So if you look at the differential equation governing the motion of the system, is going to be mx double dot plus cx dot plus kx is equal to 0. And if you were to write this equation in the state space, please note this is the second order differential equation. So one second order differential equation will give you two first order differential equations, two first order differential equations. And these are in the state space, you will start with the lowest variable, which is x, that has zero derivative, and then its second derivative, which is x dot. So you would have same thing, d by dt of x is equal to x dot, d by dt of x dot is equal to, you're going to have minus kx minus cx dot. So now your state space equation d by dt is going to look like 0, 1 minus k by m minus c by m x dot. And if you are at MATLAB, I would encourage you to substitute some values of k. Say k is equal to 5, m is equal to 1, and c is equal to 1. And you will notice that the eigenvalues will have negative real parts. So eigenvalues will have negative real parts. Are you with me so far?
Yes, sir.
Now, what does that mean? It means, think about it, that if you displace this system, what's going to happen is it's going to go back and forth, back and forth, back and forth, back and forth, and finally it will go back down to the equilibrium position where we started. So in every oscillation, the damping is going to absorb some amount of energy that will make that system asymptotically stable. Everyone understood this? The last thing which I want you to try is, say, have negative damping. So for an example, your C is now negative. What that means is your equation is going to look like mx double dot minus cx dot plus kx is equal to 0. So now what I want you to do is, in the previous expression, substitute k is equal to 5, m is equal to 1, and c is equal to minus 1, and tell me what you get. You will get positive eigenvalues.
That E times E, C is equal to negative E times E.
No, say c is minus just minus 1. So basically you will substitute 0, 1, minus 5 plus 1 and find the eigenvalues. Yeah,
So all of these give us two eigenvalues, correct?
correct.
What happens if one is positive and one is negative? What is that?
Okay. In this particular case that we haven't discussed what happens when one is positive, one is negative, but bear with me. I will explain it to you in just a minute. So basically what that means. So basically, what are eigenvalues and eigenvectors? Eigenvalues and eigenvectors give you the decomposition of the matrix. Now, what do I mean by decomposition of matrix? If you are describing a physical system in terms of matrix, if you are describing a physical system in terms of matrix, eigenvalues and eigenvectors give you a mathematical way of sort of converting that big system into small subsystems. So that is what happens when you do an eigenvalue decomposition. And if one eigenvalue is negative, which means even though you have this big subsystem, in this big subsystem, the component of that big subsystem is simply stable. If the other eigenvalue is 0, which means the other component is not neutrally stable. Now the big question is, then how does this big system behaves? Say for an example, if I have a system where the component, a part of that system is unstable and part of that system is stable, how would the entire big system behave? The entire big system will behave on what subsystem is excited. In other words, what are the initial conditions you are going to start with? So for an example, if the initial conditions are going to start or excite the subsystem that is simply stable, the whole system will be simply stable. If the initial conditions are going to excite the part of the subsystem that is unstable, that the whole system would be unstable. So basically that depends upon whether you start on the stable manifold, center manifold, or unstable manifold. Any questions? So, but I want you to try this. This is super duper important. So key point here is, how do you solve any linear differential equation with no forcing? So what I'm trying to say here is, imagine I give you this super duper complex differential equation, x1 double dot plus 3 x1 minus x2 plus x2 is equal to 0. I give you another differential equation, x2 double dot plus x1 dot minus x2 dot plus 3x1 minus 4x2 is equal to 0. And now if I ask you, I want you to solve this differential equation. What do I mean by solution of this differential equation? Solution of this differential equation is finding out a function x1 of t, finding out the other function which is x2 of t, so that when I substitute these values in this equation, the left hand side is equal to right hand side. Everyone understood this?
So I did not catch that. Can you please explain
Yes.
that again?
So let me say this way. I want to solve this differential equation. What do I mean by solving differential equation? Solving differential equation means somehow, either analytically, experimentally, numerically, or by trial and error, finding the values of x1 and x2, so that when I substitute those values of x1 and x2 in these equations here, say 3 and 4, the left hand side of that equation is equal to right hand side of that equation, which is 0. Now, can someone tell me, by looking at this differential equation, what is the solution? No. The easiest solution is x1 of t is equal to 0, x2 of t is equal to 0. Are you with me?
Nicely done, sir.
Because x1 dot is equal to 0, x2 dot is equal to 0, x1 double dot is equal to 0, x2 double dot is equal to 0, which means everything is 0. Left hand side is equal to right hand side. This is called as the trivial solution. Trivial means not important. Like Redcast Robotics 1 class. It's a trivial class. It's not important. So this is called as the trivial solution, which is not important. But if I want to find out the actual solution, which is important, here is what I would do. I would write this equation in the state space. Please note, this is the second order differential equation. This is also the second order differential equation. So I would use 4 states. I would use x1 dot d by dt of x1 dot. Actually, I should write this like this. D by dt of x1, d by dt of x1 dot, d by dt of x2, and d by dt of x2 dot. And I would write this as the big matrix. This would be a 4 by 4 matrix. And then I would have x1, x1 dot, x2, x2 dot. And once I find out the eigenvalues of this matrix, I would know whether this system is stable, simply stable, or unstable. Now, there is a simple way of doing all this, and I will actually work out a MATLAB example in next class. But I want you to understand in the very first problem what we did. The very first problem, can you see that we took an exponent? Do you see that? I took e to the power at. Do you see that? I want you, everyone, to focus here. Can you see that I took an exponent, right? Everyone understood this? So here is what I did. I had a number a. Remember that number a came from here. Can you see that this number a, actually this is a. This is a. This number a, I multiply that by t and took an exponent. And believe it or not, that gave me the solution. Once again, I repeat. The process here was, I had a scalar number a, I multiply that by t, took an exponent, and that gave me the solution. So to solve any differential equation, this is the crux of your differential equation class. Remember, only remember this. To solve any differential equation, write that equation in state space. So write this equation in matrix form. And inside MATLAB, you will do something like this. SYMS time variable, multiply your matrix by T, and you take the exponent of the matrix, EXPM A times T. This gives you the solution of your differential equation. This is the only thing that you should remember from your differential equation class. If you don't believe me, what I want you to do is assume if your A is say 0, 1, say K by M 0. Go to MATLAB, do SYMST, do EXPM A multiplied by T, and you're gonna get a big equation. And that big equation is going to be the solution of your differential equation. Everyone understood this? Once again, I repeat, from your differential equation class, even if you don't remember anything, the only thing that you have to remember to solve any linear differential equation which has right hand side is equal to 0, write that equation into state space. So find the matrix A, go to MATLAB, do SYMS A, and then take the matrix exponent. Why this is M? Because this is matrix exponent. This is analytical way of solving the problem. Now what I need to do is I need to discuss something called as the Laplace transform, and I would discuss that in detail in next class, and then I will show you the solution that you get from the Laplace transform, solution that you get from this analytical technique, and the solution that you get from the numerical technique, and solution that you get from transfer functions, and all that everything matches. But before we conclude for today, I want to ask you, does anyone know about anything about Laplace transform? Do you know what Laplace transform is? So in simple words, explain it to me. What is Laplace transform?
System, rearrange it, and plug it back into the system.
Have you heard what Laplace transform is? No, yes,
It's familiar.
familiar.
You're
Okay.
you're taking something and transforming it to something that you can use in an application like MATLAB.
Okay.
Differential equations.
All right. So I'm going to give you a very no nonsense view of Laplace transform. Here is what Laplace transform is. So before that, let me go to logarithms. Does everyone know what logarithms is?
Yeah.
Yes, no?
Yes.
What is the basic benefit or purpose of logarithms? So think about it. If you have a huge number and you want to multiply that huge number by a huge number, you're going to get a very huge number. Do you agree with me? Huge number multiplied by huge number, you're going to get a very huge number. And that's going to take a lot of time. Do you agree with me? So what do I do by doing logarithms? I take the log of this huge number, which is a small number. I take the log of this huge number, which is a small number. And rather than multiplying, I just add them. Once again, rather than multiplying, remember multiplication is going to take a lot of time. Addition is easy. So this big number, multiplication, time consuming. So what I would do, take log, take log, these two are small numbers, add them together, and I would get a number. I would find the inverse log that gives me the product of these two. Are you with me so far?
Yes, sir.
Laplace transform does the exact same thing to the differential equation. When you try to solve differential equations, it's a differentiation. So what we need to do is we need to do integration. Do you agree with me? But if I take a Laplace transform, that differential equation dx by dt gets converted to an algebraic equation, oranges plus apples. That is easier to solve rather than integrating. So by taking the Laplace transform of the differential equation, I get an algebraic equation, addition and subtraction, that can be solved very easily. And once I do that addition and subtraction, I do inverse Laplace transform, and boom, I got the solution of the original differential equation that I was looking for without doing integration. Everyone understood this? That is the fundamental purpose of Laplace transform. And we are not going to look at different types of Laplace transform pairs. I would just tell you, given a Laplace transform, how to use Laplace transform and how to find solutions. Okay, I'm going to stop here and we will continue the next class.
Regarding similar
Yeah, angle of the second theta, theta dot, or the first joint. Variable A is the distance.
Oh, I think so. It's for the assignment.
Yeah, and I will actually explain that assignment in next class and solve it partially. Not in next class, next to next class. Next class I have to finish Laplace transform, but I will solve assignment 5, problem 1 partially.
The due date is changed for assignment.
Huh?
The due date.
I changed it all the way to 30.
I guess you got all these 3 assignments beyond 30.
Yeah, but
Even the
basically
projects.
there are 2 assignments. What?
They are on MATLAB.
Yeah, they are just on
Oh.
MATLAB. Yeah. Question?
I'm not able to access the Simulink